Don't worry, we'll get to that. The parameter used to count running time is usually like the whatever variable you're looping over. So if you have an input, it's usually like what you're taking as input. So your program might take like a number, like the size of like a list, and then you would treat the size of your list or that number as your input. Where will the recording be posted?
Several places. It'll be on our Discord and our Instagram.
Okay.
And it will also be on our YouTube.
Yeah. Okay. With that out of the way, I think we're good to start. So, hello. Welcome to the CSCA08 Final Exam Review Seminar by Katrina Best and Alex Teeter. Let's kick it off. Let's go to the first slide. Right. So what we're going to be doing mainly today is we're going to cover the generating a new story. Why is the selection function counted with the assignment statement and the selection sort function counted with comparisons? It's counted with those because those are just steps of the program, like doing something. We don't distinguish with the type of steps between the type of steps the program does. We just count like a step as like one. Basically, we just look at the steps the program does. Anyways, okay, so the main topics we're going to cover today is generating a new story, unit testing, and sorting algorithms. So stuff like selection sort, insertion sort, and bubble sort, and we'll also be covering time complexity as well. So hopefully we'll be able to answer your questions then. Right, so we're going to go over the generating a new story exercise that appears very commonly in A08. So we're just gonna go over a quick review of the dictionary type in Python. So if you remember, the dictionary data type stores values in key value pairs. So it's important that the keys must be an immutable data type. So they can't be lists because you can go in and change a list, and that's kind of bad because you don't want your keys to be like changing while the program's running. That would not be very good. So out of like program like safety, like they made it so that your keys have to be immutable. So anything can be stored as their values. So the values themselves. So if you think of the key as like going into the locker and what's in the locker is the actual values, anything can be in the locker. So they like you can have immutable, you can have non-immutable data types in your locker. You just can't have the keys be mutable. So anything can be stored as values. So you can store other dictionaries, you can store lists, anything you want. Just the keys themselves have to be mutable. Yeah, and data storage will be covered in CSCA08, if you're curious about that. So it's also important to remember that for a dictionary, we use the sort of like curvy braces and well, like with the sharp endpoints and not like those other two. Those other two are used for lists and tuples respectively. So that's an important difference to remember for when you write your programs. All right. If nobody has any questions, I'm going to go on to the next part. So here's generating a new story. So here's some examples of dictionaries. So in the first dictionary, we're using strings as our keys. And remember, strings with the double quotes are immutable in Python. So these are valid keys. And as you can see, we're storing our specialties, basically our majors. And then we have cool profs. So Anya, Anna, and Natalia, again, we're using strings with the double quotes. So they're immutable. And we're storing strings also with the double quotes. The courses the professors are teaching. And finally, we have pair to pair, which instead uses tuples of strings as our keys. And if you remember, tuples, unlike lists, they're immutable. So these are also valid keys. So remember that you can use tuples as keys, just not dictionary, or just not lists. You cannot use lists as keys. And as you can see, it's just we're pairing things up. Okay, so here's some useful methods for dictionaries that will help you a lot. These might appear on the exam. You might be expected to know these. So a .get is a method on a dictionary that will basically give you the key value or the values at a key. So for example, if I want to access like what's stored inside the locker that has Alex as the key, it will be math and CS, right? Because that's my those are my specialties, my majors. That's what's behind the that's what that specific key value pair is. And you can also do dot values, and this will basically return all the values in your dictionary. So not the keys. The values are the stuff stored behind the keys. So in this case, if you were to run values on Google Profs, you'd get all the courses they teach, but you wouldn't get any of the keys. So is that clear? Does anyone have any questions about that, or are we good so far? Okay, we can go on to the next part then. Okay, so sort of the main idea behind this is we want a program that looks through a text file, and it uses a certain number of words as the context, and then it generates a new story using that context. So here's an example of a story. So we have Alex and Katrina are cool, Alex and Katrina are awesome. So each time we sort of store a context, so the context for the two words would be Alex and then basically all the stuff that comes after that pair, whenever that pair appears in the story. So Alex and only appears once in the story, and Katrina only appears once. But if we just use dict values, Python will output dict as yeah, you have to loop over it. Yeah, because it outputs like a different, yeah, so you have to loop over it. Alex and Katrina are cool. So again, so we have Katrina R. Katrina R appears twice. So it appears once here, once in the first part, and once in the second part. So we have two words that form the context list of this pair. Next we have R cool. R cool only appears once and has Alex after it, and same for cool Alex. So each time the program will go through a list of words after the current context, it will print a word, and then it will create the new context from the last word of the previous chosen context and the new word chosen. So basically, it's going over a list of words like after the current context. So it's gonna just randomly pick one word, and then it creates basically. Then it basically picks a context. It finds, oh, which context are we in now, and then does the same thing basically. And if the new context isn't in the dictionary, we just choose the random context to be our next. So if, like, for example, if we're at the end and we don't have the context for example, we don't have the context for our awesome, but so we'll just go back to some random context and continue from there. So that's just the main idea behind that.
Can I also add something?
Sure.
So, just to clarify, you see how there's like and, are, and cool are capitalized? That's a mistake on our part. These are lowercase and it's case sensitive. So if you were to try and do like a lowercase and then Katrina is capitalized, you wouldn't get a key in here. So make sure that these are lowercase and the names are the only things that are capitalized. Yeah. Do you want the next slide?
Sure. Okay, so we want to use the correct data type for generating the story because we want to make sure the tools we're using are well fitted to the task. And so the dictionary of tuples and then lists is the obvious choice to go with here because that was the motive. So the motivating sort of idea we had in the last slide, that's basically what we're trying to do. Well, the data type that's most suited to that goal is the tuple to list data type. So because as you can see, we can store our tuples as keys, and we want tuples to have like a specific ordering on them. So that's also good for our purposes. They're immutable, so they can be used as dictionary keys. And we can do the whole like storing like context words as lists, which will help us in our goal of creating the story. Does that make sense to everyone? Is that clear? Is it clear why we use that data structure? Okay,
Awesome.
good. Okay, I think we can go on to the next slide. Okay, so basically we'll store each word in the file in a list. So This basically gives us a really easy way to see what words comes after each, because remember, in a list we can kind of just go through and then like do 0, 1, 2 to like access the first element, the second element, the third element, etc., etc. And so this gives us a nice like induced ordering on each word in the each word in our like our original file. So then we can use that to generate the context. So as an example, we had our story in the sort of motivating sort of like we had this huge story and we broke it into a list. So if you remember, there's a function you can use on file objects. It's the read, so you use the read first. That allows you to just like actually get the file object from your file name, and then afterwards you can use the split, and split will split automatically breaks it at each space. You can add other stuff to it too if you want to break like at maybe you want to break it commas, you can also do that too. But for our purposes, just splitting at spaces is fine. Does that make sense? Is everyone familiar with that?
We'll also go over each function in the next slide.
Yeah. But that's clear to everyone, right?
Hopefully.
Yeah, hopefully. Okay, I guess we'll go on to the next part then. So, so first of all, so we're gonna have a function that's just called read words, and this just basically does what we've discussed already. It will literally just return the list of words from the story in the order they appear. It's important to note that we're assuming that a file is already opened for reading, so don't reopen or close the file within the function because we're assuming it's already a text.io file, meaning it's been opened already. So this is sort of like it's sort of very subtle, but it's important to remember. If you're assuming you're getting a text.io file in your function, just assume it's already been opened for reading, and don't modify it within the function. It's just sort of like a best practices thing because you might want to like read others like read again from the file maybe in your function, and it's like if someone else is using your function, you don't want to like because people will basically just be assuming your function only does like one thing and it returns this list. They don't want to like have alternate effects like closing the file, like that could cause issues. So if your function's given a text.io file to begin with, just assume it's already been opened. Don't try to open it yourself. Don't try to close it yourself. Uh, for your purposes, it's off limits in that. It's off closing or opens off limits in that function. So remember, read returns a string of all the contents in a file, and split just splits the strings over some optional parameter. By default, this is just a space. But does that make sense to everybody? Is that clear?
Oh. Also, just to recap, who remembers what read line, and read lines does and the differences? Yep.
Yep.
Read line is for each line. Yep. And there's a pointer. You don't have to worry about pointers, but there's essentially an imaginary thing that's going through each one. And read lines returns a list of lines.
Yeah, I'll give you a list of the lines basically. Yeah. Good job. Okay, I think we can move on to the next part.
Also, so for Edison, no. If you are given a file that is already opened, you do not open or close it. It's just customary. It's one of the best practices because if you start closing things and reopening them, you might mess up the rest of the system where this function is actually being called. Yep. Also, just a word on what else we're going to be covering. I think after this presentation, I'm going to go over the exam from last year. So stick around because I know this is just a slide, but we will be like coding through last year's exam. Okay.
Yeah, so here's the sort of here's the build context to words. So this is what actually builds our tuple and then list of strings we discussed before. So we initialize the context to words dictionary, and then we loop through the range of our length of our word list, so minus the context size. Yeah, and so this basically so we go through, right? We create our context, which will basically just be like, oh, we'll section off like into like two parts, right? So for this, we'll, for example, in the story we discussed before, and how we discussed we were going to do it before, we had two words, so two words form the context. So you'll go through the line, and it'll be like two words
Those
each time.
times, right?
So yeah, like that exactly. And you'll go, yeah, like you'll look through the program basically looks through the sentence, and it goes two words at a time, and it will go up to the sentence minus two times like your context size. In this case, it's two, so you're not gonna like go past, like you're not gonna go out of the list. So that ensures that you always stay inside the list when we're doing this. Yeah, and then so after that, so wordless I plus context size. And then so afterwards you'll go back into your words list. So and then you'll add I plus the context size, and this will basically this basically adds so you're at a current context, right? And then you have a word that's next to it, right? So that's your context, and then the word that's next to it will be added to the context list. So if your context size is two, then if you add two to the current I you're at, you'll go to the word that's next to it. And then afterwards, so the context is the key. Remember, the context is the key to our context words dictionary. And so if context is in context to words, we're just going to add to that key that's already in there. Because remember, we could have like the same context show up twice, right? Like in our example before, we had I think our awesome had two showed up twice in the sentence. So if the context is already in the dictionary from going through the loop earlier, then we're just going to append the word onto its list. Else we're going to, so remember with dictionaries, if you add in a key that hasn't already been initialized, it will just create that key for you. And we're just going to add in the list containing word. And yeah, that's basically how we would go about building the context towards dictionary. And all we have to do now is actually program something that basically builds the story out of the context towards dictionary. So that was a lot. Does anyone have any questions about how this sort of like works?
I also just added, remember slicing is inclusive for the first number and exclusive for the last number. So for, in this case, the context, when we're creating that tuple, it's going to be word list. The first iteration will be 0, 0 plus 2 for this example. So it's going to include position 0 and position 1 words.
When we do split, do we have to do strip? Strip was the one that gets rid of the stuff, right?
The slash ends, yeah.
Yeah.
I think you would do that during this part.
Maybe
Because for split, that is separating it based on the delimiter, which would be space by default. Yeah, I guess you would have to, because it would be added. The slash n would be added to each last word. Yeah, so you would do strip at the very end.
Yeah, just to get rid of the slash ends. Yeah. Yeah. So we would do that, yes. Yeah, because you want to get rid of the slash ends, yeah.
Yeah.
Because that will appear when you read the file. So yes. You want to strip off slash ends. But is everyone like okay with this sort of program? I know it's like really large, and maybe this is a lot to take in.
Yeah. I bolded the code, so the code's bolded, and then the comments are kind of
Does Natalia, or not Natalia, does Anya always do like an example like, did Anya do an example like this semester? I know she usually does something similar to this. Because when I took the course, we did something similar to that. Okay, yeah. So you all have seen this before. Okay,
Okay, good.
okay, okay.
Um,
All right. I think we're good to go into the next part.
I
In the
just want to
previous
add,
slides, do we have to add strip?
you would add it here.
Yeah, you would
So
add it here probably.
split, it's an automatic function in Python that would split it. So it would have the slash in on the ends of the last words of each sentence. But in this, when you're building the context to words, right here, or when you're even defining word, I would do dot strip here.
Oh, why is it length of L minus context? It's length of the word list minus the context, because remember, we're sectioning these off into like context blocks. So like, for example, if it was size 2, oh, in class, it's length of L minus context minus 1. Length of L, context minus 1. Len L, length of the list minus context minus 1.
Oh,
Yeah.
yes, it would end at that index. Yeah.
Yeah, but remember the range function I don't think is inclusive, so it won't include the end. It won't include the end part. So yes, you are right. It does end at index length of L minus context minus 1, but remember the range function doesn't include the final thing basically. So you'll go to the thing before it, which is -1, but then you won't go to the actual like length of word list minus context size. But the reason why you have minus context size is so you don't go over like you don't like accidentally go outside the list. That's the main idea. Okay, is that clear? Can we go on to the next part? Okay, awesome. Okay. Okay, now we're gonna actually build the story. So we have all our parts, we have everything together. Now we just have to build a story string. So we're gonna get our content.
Sorry.
No, it's okay. Yeah. So we're going to build our context. We've already built the function, so we can just use that. Right? Always good to modularize your code. So we've already built all the tools. We were just putting them together now. So we're gonna build the context. So we have the context word dictionary. This so far is empty. We're going to build it using get random context. So, or no, we already have the context words dictionary, and we're sending in get random context just to give us a random context from the context words dictionary. And then for in the range of number of words, right? Because we want our story to be a certain number of word size, right? Which we pass into this function. We're gonna get the list of available words, right? Which is sort of the words within our context we're currently working in. And then we're gonna choose our next word to be a random word from this current context. And then we're gonna add this word onto our story. And then we're gonna create a new context. And the new context is basically just the last part of our we take off the first part of our context, and then to replace that, we add on the word we just added into the story, and that's the new context basically. And then if context is not in so if the current context we built from adding on that last one is not in the dictionary, we just get a new random context. Otherwise, we just keep looping and looping and looping, doing that same process until we've built a random story. And from this, we have a very crude random. What does get random context do? Yeah, so you remember how we had like a context word dictionary? So we had each of our contexts and then we had a word. So what get random context does is just selects a random key from that dictionary for us to use for building our story. So
Yeah.
all it's doing is just getting a random key basically from the dictionary.
Yeah.
Yeah, it's a helper function. Yeah.
I believe there's a function just in dictionary to get a random key too.
Yeah, you could just so
Not
it is
built
not
in.
built. No, it's not built in. But you can like honestly you could just do get random key. There's probably a built-in function in Python to do that.
Yeah, I'm pretty sure there's a library called random. You can import that and then just do a random dot sample.
But is that clear? Is this clear now? Hopefully it's like, hopefully at least the main idea is like clear here. We're basically just look at a random context, pick one word that's in in the context list in the dictionary, then build our new context by deleting the first word in the context and adding on the word we just picked, and then sort of do that same process. If the context we built is not in the dictionary, pick a new random context, on and on and on, basically. Is that clear? Okay, I think we're good to move on.
Okay.
Okay, and then yeah, here's basically our here's basically the full function now. So we've had all words, so all words just reads the words in our data file. We build the context words dictionary, and then we basically return the generate story function, which we've made in the previous slide. This is just the thing that basically runs all our functions using some data file with a preferred context size and a number of words. And then there you go. It will return a random story. There's not too much to this function. We're just running all the stuff we built already to do the random story. Is that clear to everybody? Does that make sense?
Also, just for the random question, you can change your diction, like you can get all of the different keys by doing just dot keys. And then you convert that to a list, and then you can call the module called random. You can do random dot choice. Here is kind of an explanation of that if you need it, but yeah, that would be a helper function.
Okay, so I guess we can go on to the next part. So unit testing. So basically, unit testing provides you with a more sort of robust way to test your functions than doc testing, because doc testing is kind of limited, right? Because they're like, you can only look at a certain amount of certain types of objects very easily, and then for like other types of objects like dictionaries or if you want to check if something's changed, it's very cumbersome. So for the purposes of this seminar, we'll look at the following two functions. So return list. So we have a new list, and then we have an input cool list. And for object in cool list, we're going to append. So we're going to append to our new list object +1. So it's a list of integers, so we can add numbers to it. And then we're going to look at the function modify list. And this will take in as input a cool list and return nothing. So for index in range length of coolest, it's basically just going to set coolest index to coolest index +1. So these sort of do the same thing, except one will not modify the list. It'll create a new list with a one added to everything, whereas modify list will actually like change the list itself. It's important to know the differences between these two functions. It's very subtle, but it is important. One modifies the existing object in memory. The other one will create a new object in memory with one added to everything in the original list. Does that make sense? Is that clear? Awesome. Cool. Okay. Next part. Okay, so remember when we're doing so this is how you sort of set up the doc testing. Don't worry too much about what a class is right now. That's not
Yeah.
important for this course. It's just something you write in the unit testing. You'll learn more about what classes are in A48 and B07. But for right now, just pretend it's just there for black box reasons. So we have an actual value. So remember, we want to look at return list 1, 2, 3 as our actual value. So this is the value actually returned with this as our input. So think of this as just one test. So this is just one single test. And we're looking at the expected value. The expected value should return a list with 1 added to everything. And we have the message. So the message will be return list 1, 2, 3, and then we'll have the actual value in the message and the expected value. All this does is just prints out a message or creates a message, basically a string based on all these stuff. And then we'll display, we'll test. So self assert equal will basically test the actual versus the expected, and then spit out our message, spit out the message after. The message will basically show like what we got for actual and what we got for expected. And if self assert equal does find their equal, then the test will pass. Otherwise, the test will fail. And that's basically how you set up a unit test for this one case. Then there's the other case of mutating objects. That one will be a bit
We'll
more
go through that, yeah.
difficult. Yeah. Okay, so here's the modify list test. It's a bit more, it's slightly more complicated, but we're still doing the same idea. So we have the actual value will be 1, 2, 3. That's just the list we're passing in. And we want to pass our actual value into modified list, so it gets modified. And then we want to check that against the expected 2, 3, 4. So the difference here is that we're not when we have the actual value, we're modifying the actual value instead of creating a new value as our actual value. And we want to just check that this actual value is modified correctly instead of copied or instead of creating a new copy correctly, we modified the original actual correctly. It's a very subtle difference. But everything else here is basically the same. So everything else here is just doing your normal unit testing stuff. Does that make sense to everybody?
So just in summary, for non-mutating, you set actual equal to the return value of your function return list, and then you create expected, and then you compare the two. For mutating, you set the actual, the original list to a value, and then you modify that. Note that this isn't set to anything because the return value of modify list is none. If you do, you're just going to get the object none, and that's going to be incorrect. And then you still create your expected list, and then you compare those two now. So the actual is being set to a variable.
Yeah, remember, so a lot of people make this mistake in A08 midterms and exams. That's a really good point, Katrina. Functions that modify will not return anything. So if you set actual equal to modify list in this case, you'll get none. So the test won't work properly. So remember, modifying functions don't return anything. They just modify the original object. So if you set another thing equal to the function, well, the function's not returning anything. So your test won't be correct. And also, a lot of people make this mistake too on other questions that have modifying functions. Be very careful with that. Be very careful between the difference between modifying something and a function returning a new thing.
Yeah.
Okay, yeah, I think we can go on unless anyone has any questions or there's any confusion. Okay, so time complexity number 1. So this is going to be a very like simplistic like look at time complexity. In A48 and like more other courses, you'll look at a more robust, like you'll look at more robust version of this, but we'll just go over like some simple time complexity analysis. So for here, we'll just be looking at constant time, linear time, quadratic time, and polynomial time. And time complexity will basically just tell us how fast an algorithm or how much an algorithm runs given an input. So what you can think of is your program is like a function, and it takes in maybe an input x, or maybe x is the size of your input, and it will output some other, maybe it'll output a polynomial or it'll be constant. And we're just looking at how the amount of steps is related to the amount of steps is related to the input. Okay, let's look at some examples.
Okay.
Okay, so we have a regular for loop. So if we have a list of k elements, then if we input the list and we loop through its elements and maybe we do something, right? This will have time complexity k. Why does it have time complexity k? Because we're doing k steps. Because remember, we're looping up from I to k. So that will be going k times with respect to the input, right? So if I input a list of length k, we'll loop k times. So for example, let's say the list is of length 3, then we're going to loop 3 times. Or the list of length 4, we're going to loop 4 times. Or the list is of length 8, we're going to loop 8 times. Or in general, if the list is of length k, then we're going to loop k times. Some loops can have a constant running time. So let's say we inputted like any list to this loop, but we didn't like actually use the list as a range to loop over. So we just did for I in range 3 dupe thing. This would always have a time complexity of 3 because no matter how big the list you input, you could input a list that's 100 elements, 1,000 elements, 1,000,000 elements, a gajillion elements, a centuplet of elements, whatever, however big you want to get. This loop will always go just for 3 times. It will never um it will never
It's not dynamic. It
yeah, it
doesn't
will never
change.
change with respect to the input. Yeah. So that's sort of like that's the idea behind constant complexity. We can also cut complexity in half. So for I in range 0, length of L, and then so remember you can skip over, right? You can do skips in your range. So the third input to the range function basically just says, okay, skip over every second element in that range. So this means we're only going to be going through half the length of the list. We're going to be having the amount of stuff we go through in the length of the list. For example, if we input a list of length 4, we're only going to be going 1, 3, and then ending, right? So that will be 4 over 2 steps, which is just 2. Or if we input a list of length 8, that'll be 4 steps, or a list of length 16, that's 8 steps, or a list of length k, that's k over 2 steps.
Yeah.
K over 2 is still considered linear. Yeah, it's still considered linear. A complexity theorist would basically just say that, like, yeah, this is order k time. I think for the purposes of this course, she wants you to like specify whether it's k over 2 or k. But in general, in complexity theory, they don't like really distinguish between k and then k times a constant. But they do distinguish between like stuff like k squared and k, because k squared sort of like dominates k. It's like it's much larger as the input gets large. So you do distinguish between k squared and constant time. But
Mhm.
technically, no, you would not need to distinguish between k and k over 2. For the purposes of this course, she wants you to give like the exact complexity, not the complexity class. So I would say on an exam, it's good to know to distinguish between k runtime and k over 2 runtime, even
Yeah.
though in the eyes of a complexity theorist, they are technically the same order of running time. Yeah, does that make sense? So k squared plus k will be quadratic runtime, right? Yeah, good question. Yeah, so it will be quadratic running time. And you can
Oh,
see this. You
sorry,
always
just to note, make sure that k is not constant in this. K
yeah,
is the length, or sorry,
yep.
k is dependent
Mhm.
on the
Yeah,
list.
so the general idea is you always consider the highest order term in your polynomial. Um where mk is real. Yeah, exactly. Yeah. So for any real number m times k, no matter how big m is, mk is still linear. It does not matter how big m gets. M could be 1,000,000, billion, however big. That's
Yeah.
still linear time. Yeah. Um you'll learn more about that in B63 and C63 and C73. But for now, just focus on the fact that it's a function on you. Where do you find time complexity problems? There's plenty of good time complexity problems probably online. I don't, does Anya give worksheets?
I think she still does.
Okay. Another good thing you can do actually, and I encourage you to do this, is go through all the worksheets before and like all the algorithms you coded and try to find the complexity of those algorithms yourself. That's actually a really good exercise as well. If you don't feel like necessarily comfortable with time complexity, that would be a really good thing to do. It's also a good review for like you kind of you kind of like knock two birds down with one stone because you're also reviewing through the previous course content, but also you're looking at it through the lens of complexity. So maybe that would help sort of drill home not only complexity, but the you'll remember, oh hey, yeah, for this part of the course, I did this thing. Yeah. Is that an okay answer to your question?
Actually, I just found I'm just sending it. So this is from her website. It's runtime complexity examples.
Hmm. Also, another thing you can do is I think the past exams have runtime examples, so you can look through those too
Yeah.
in the repository. Yeah. Okay, is that good? Does everybody understand this so far?
I hope so. Okay, we're gonna keep moving on, and then we're gonna take a small break after we finish this, and then we'll go to complete the last exam.
What about loop composition? Right, what if we have nested loops? So let's think about this. So this is the most like simplest example. This is two nested loops with the size of the list basically in the range of the size of the list. So let's think about this intuitively. So we have a list of length k, right? And we're looping through I up to the length of the list. And then for each loop I, we're looping in j for the length of the list. Why does insertion sort depend on assignment while selection sort depends on comparison? Yeah, so good question. So in general, we don't distinguish between the types of steps. So a step is just one. So you're just adding one to the amount of stuff you're doing. You don't distinguish between what that step is actually doing on like a maybe those are like different like on a hardware level, but to a complexity theorist, you don't generally care about like what the steps are actually doing. You just care that there are steps. There you are doing steps. So you don't really distinguish between the types of steps or what you're doing in those steps, just that those are steps. Does that make sense? You kind of treat like all steps the computer's doing is like the same or as equivalent. So that's why insertion sort depends on assignment, while selection sort depends on comparison. Because doing an assignment and doing a comparison to a complexity theorist, those are equivalent. What about for I in rangeland L? That's what we're looking over right now. Or did I
That's
misunderstand the
linear.
question? Oh yeah, that's linear. Yeah, so we went over that last slide. So that would be linear. Yeah.
It's
So sorry, I didn't want to interrupt.
no, you go ahead.
Yeah, so let's think about this intuitively. So let's say the length of our list is 2. So we input a list of size 2. So for I in range 2, so we're going 0, 1, and then for j in range 2, we're going 0, 1, right? And then for each I, so we're going 0, 1, which is 2 steps, and then 0, 1 in the j loop again for the second iteration of the I loop. Starts at I like in the adding coins. What happens with the second loop starts at I? Yeah, so we'll sort of look at an example like that. So, but basically you would have that would have the time by I believe I think, or you would subtract time I from the time, but it would still be squared. But for this simplistic example, right? So this would be we're doing 2 steps for each of the 2 steps we do. So it'd be 2 times 2, which is 2 squared, which is 4. Or for example, if the length of the list was 4, we'd be doing 4 steps for each of the 4 steps we're doing. 4 times 4, 4 squared, that's 16. And then in general terms, if we have a like length of a list of size k, then we're doing k steps for each k iterations, that's k times k squared. So does that make sense? Okay. So for example 2, it's the same idea, except our inner loop is now not dependent on the size of the list. So for example, if we have a list of size 2, right? So we'd be going, so for coin index, um,
I think they're trying to determine whether or not it's quadratic or linear, just because
Oh,
that
okay.
second for loop is different. Like it's only
Yeah.
going through from the first coin index one.
It would still be quadratic, and the reason why it'd still be quadratic is that it's still dependent on the size of the list in the second loop. So even though you're not looping over the whole list in the second loop, you're still looping, it's still dependent on the size of the loop for each iteration of the outer loop. So it would be k times k minus something, probably k minus the coin index, or k. I don't know the context for this question, so I don't know what exactly coin index is supposed to denote, but yeah, that would still be quadratic.
I also added the old exam repo. However, AO8 used to be taught in the programming language C, which is what A48. Oh wait, is it, or was it A48 was taught in Python? Might be
A48
the
used to be
opposite.
taught in Python.
Never mind. Ignore that then. AO8
It
should be.
still is at the other campuses. I think we're the only campus who like teaches it in C.
Of course we do.
Um, but yeah, so for example two, right? So we have an input. Let's say we have a list of length k or length 2. Then we'd be looping 3 times for each iteration. That's 3 times 2, so that's 6. Or in general, if we have a list of length k, then we're looping 3 times for each of the k iterations. That's 3 times k, or 3k complexity. Is that clear to everybody?
Um, yeah.
It sums the coin with the other coins in itself. For coin index 1 in range denoms, for coin index 2 in range, coin index 1 len denoms. Coin index 1, yeah, that would still be quadratic. Because you're going through each like index in like the length of that list, right? That's still the second loop inside of it is still dependent on the length of the list. It's not going through the full list in the second for loop, but you're still going through over a part of the list for each part of the list you're looping over. That's quadratic. Does
Oh,
that make sense? I know it's hard to think about, like I know it's sort of hard to think about that kind of stuff, because it's like, oh, you're looping over a list while also looping over a part of the list. So
but it's less. But yeah,
yeah, you have
what
to.
Alex, so for
Yeah,
that second for loop, just correct me if I'm wrong, but the amount of steps that's going to, or the amount of comparisons that are going to happen in that second for loop is going to be the length of denoms, but exclamation mark.
I think so. Yes, I think. Um, I've actually not seen this example before. Uh, like sigma 0 to k. Yeah. I
Yeah.
think I think that's correct. Yes. Yeah.
And since we removed the constants in time complexity, except you would still add it for AO8. AO8, she still wants constants, I believe.
Yeah. But yeah, I think you're correct in saying it's sigma 0 to k of k times k minus I. Yeah, that would make sense because you're looping over each of the indices, and then for each of those indices, you're looping up to that indices. So that would make sense. Yes. Yeah. So it should be sigma 0 to k times k minus I.
Yeah.
Yeah. Okay, I think we're good to go on to the next part.
Okay. Oh, sorting algorithms. Awesome.
Yeah. So we have selection sort. Do these past tests not have solutions? They don't have solutions, unfortunately. I wish they did, but
Me too.
unfortunately, the stuff in the past exams repo don't generally have solutions.
But we are going to go over last year's exam, which is like the most recent. So we will go over the answers for that and we'll code it together.
Does selection sort always check the entire unsorted list?
Yes,
Yes,
it
because
does.
you're always
Yeah.
picking an I value, and then you're like looking for like the one that's like smallest, the smallest of it, basically. Yeah.
So, yeah, so there are certain sorting algorithms that are better, some are worse.
Yeah.
And we'll be going through each one as well as an example and the
Hmm.
explanation of it. So by
Yeah.
the end of this, you will understand all three of these. Don't worry.
Yeah. I thought insertion sort had a best case. Yeah, it does. It
Yes.
has a linear best case. Yeah. Um, but this is a good motivation too for why we care about complexity, because sorting is like a very practical problem. Like you, many times you'd want to like be able to sort something because it once you've sorted something, it's easier to like search through and you can look for stuff easier. So being able to sort stuff is important. Uh, and it's one of the reasons why we care about time complexity. So as you can see, um, all of these are sort of how is best case linear? We'll
We'll go
see.
through an example.
We'll see. We'll see. Yeah.
Is everybody still good? Like, we can still keep going. Do you want to take a break? Like, we'll take a small break after we finish these slides and then we'll
Yeah.
go through, but
Yeah.
everybody's still good? Okay, I'm gonna assume yes. Okay.
Okay. So basically what selection sort does is it finds the smallest value in the list from the index I to the length of the list, and then swaps that smallest value. So basically what we're doing is we have an index I, right? And then so what we're doing after that is we're assuming that the other part of the list is sorted before I. And then what we're doing afterwards is we're looking for all the stuff after I, and we're finding the smallest value in that part, and we're swapping it with the ith index. So if we go from I equals 0 to the length of the list, what this accomplishes basically is that it it will basically give you a full sorting of the list, because before I, you'll always have a fully sorted list from this process, and then afterwards you'll just loop through the rest of the unsorted list, and this will give you a fully sorted list.
So, yeah, so this is the code here.
Yeah.
So for the first part, we go through the length of the list, and then we have two functions. So we have get index of smallest list, and this is also going to have the complexity from like the beginning of the list or whatever index we're at, but we still have to go through the length of the list. So it's still dependent on this variable, length of list, or k. That's why it's k times k, which is why there's never a best case scenario, because even if it's already sorted, you still go through the entire part of the unsorted list before
Yeah.
you go back. So there's never a best case scenario. It's all good, always going to be quadratic.
Yeah, exactly. Yeah.
So yeah, so essentially you go through the length of the list, you find the index of smallest each time, and then you switch. So this is like a shortcut to switch two values, but you set the list of the index of the smallest, which is in the unsorted part, with list at position I. So like the first iteration you go through it, it's going to be 0, and you switch those two places. And then you go through it again and again, and you keep going through the unsorted list until it's completely sorted.
Yep, what Katrina said basically.
We will go through insertion sort, don't worry. So this is kind of an example, best and worst case, because they're both the same. So pass one, we're going to look at like the entire thing is unsorted right now. So we're gonna check and we're gonna keep going through the list. The smallest number is 0. So the index of the smallest value is going to be 1. And then we switch that with whatever was the first value. So we switch it with 0 and 6. And then we keep going. So the blue is essentially what's sorted. And then yellow is the smallest index, or the smallest value. And then we find that index and we keep switching it until we get all the way through.
Yep. That's basically how selection sort works. Does anybody have any questions about that, or is that clear? Is it also clear why there's no like best or worst case? Like it's always n squared? Okay, okay, I think we're good to go on. I think everyone understands.
Hopefully, yeah. Okay. Okay.
Okay, insertion sort. So basically what insertion sort does, it starts at the beginning of the list. It moves the, so it moves towards the end and it inserts the ith element in the correct position in the sorted part of the list. What do we mean by inserts in the correct position? Well, basically what we're doing is we're looking through, right, the other part of the list, and we're looking, okay, is I less than that element? Okay, good. We're gonna go into that spot. Is I less than the next element? No, we'll stick there. Otherwise, yes, we'll move back. And basically what this accomplishes is that we're sort of like we're taking I and we're sticking him in the right place. We're basically sticking him in the right place before him, basically. And what this accomplishes is, again, a fully sorted list. Right. So values is list, so the value is always the list at the ith position. And basically what we're doing is we're slotting him through, we're going through, we're checking, is list I minus one bigger than our current value? Yes, then we're going to slot him into that spot. And then we're setting I equals I minus one, which means we're checking the next place. And then we're continuing to swap his values until we've got him inserted into the right place.
Yeah. And it's important that you say I is greater than 0, not I is equal to 0, because then that first value is going to be out of range.
Yeah. Is everyone clear on how that works?
And we'll go through a best case scenario and a worst case scenario. So don't worry about that. Yeah, okay.
Okay. So here's a worst case insertion sort where the entire list is basically just unsorted. Like it's actually in the opposite order from what we want. So we'd have to like go through and like slot, like go all the way back, like slot everything all the way back for each I. As you can see here, you would have to keep doing comparisons up to the starting length of the list. So the worst case is where the list is sorted in like the opposite order.
The yellow is the comparisons, and then blue is already sorted, or dark black, or whatever you want to call it. So this is quadratic, because every time that you go through, you have to go through the entire list just to move them down. Can we go to the best case scenario?
Yeah. And then the best case scenario, as you would expect, is just a fully sorted list because, well, then we don't have to like everything's already slotted in the right place. So the number of comparisons we have to make is like one for each. So it's still just linear time basically because we're just going through each element, and we already know the stuff before it. It doesn't need to be slotted in because the stuff before it are in the right order already. So, and it's not going to be slotted in with anything, so it will be linear time.
Does that answer your question, Peter? Like why best case is why best case is linear? Okay. Well, hopefully. Okay, well, we only got one more, and then we'll take a small break, and then we'll go through last year's exam.
Yeah, so bubble sort, it's kind of a meme because it's really bad. It's basically you go through and you look at every single pair for each I in the list. You look at every single pair, and if the pair is in the opposite order of which you want, so if like the first element in the pair is bigger than the second element in the pair, then you swap them, and you do this basically for. But bubble sort is the most intuitive way to sort. It is the most intuitive way to sort, but it's probably not the best way to sort because it will take a lot of time. Like it's n squared, and that's really like it will always be n squared. There's no worst or best case, and it will spell like if you think like for example if you were making a search engine and you need to sort all the search results by bubble sort. That would not be a very good search engine because it would take too long to do anything productive. Yeah. I mean, technically speaking, all these sorting algorithms aren't really great. You'll learn better ones in A48 that use recursion, uh, and those will be much faster
But don't
comparatively.
worry about recursion right now.
Yeah, don't worry about recursion. You don't learn recursion in this course. But just for your own curiosity, uh, most of these sorting algorithms aren't great. Bubble sort's probably the worst. Um, but yeah, it kind of goes to show. So in computer science, sometimes the most like intuitive way to do something isn't always the best way to do something, because the most intuitive way will usually result in more steps. And a lot of computer science is sort of like figuring out really creative ways to try to like avoid those steps. So a lot of like complexity in algorithm theory is like finding more like creative, like thinking outside the box ways to do a task that, given the sort of intuitive way we'd normally do it, would be much slower. Yeah, does that answer sort of that question slash comment, or
And the reason why we also care about time complexity is because let's say this is in a practical sense. Let's say you're building a website and you want to go over the users or something, or find a user, or you want to sort the users by last name. Depending on how many users you have, you could have like millions of users or billions. And that can put such a big load on your CPU. Like, and yes, you can do it. You can buy like several computers to do these big calculations, but you want the most cost effective and cheapest way to sort because
yeah.
that's how you're going to use it in the industry.
Because like think too, like here's an example. If you're developing a video game and you need to like constantly do these sorts like over and over and over again, right? Maybe one bubble sort's not going to do much to the CPU, but like 100 bubble sorts or like 1,000 bubble sorts, like because of your if your code needs to like sort a ton of things in a really quick amount of time, then the amount of cost on your machine using bubble sort will quickly like grow and grow and grow like exponentially compared to if you used a more more robust or better sorting algorithm that gets the job done faster.
Yeah.
So it might not matter in like a case of a single sorting algorithm, but it will definitely matter as things compile. Anyways, here's the algorithm for bubble sort. It basically just bubbles up from I to the range of your list. Um, it starts at 1 because you don't want to start at 0. Right, yeah, because you're doing I minus 1. Yeah, so you wouldn't want to do like you wouldn't want to get like index minus 1 because that's not that would be at the end of the list, but you don't want that. And yeah, you're basically just looking. Um, you're basically just running bubble up for I in the length of your list to 1, and you're slowly bubbling these things up. You're going through each time for the size of the list. You're looking through every single pair and you're swapping them around. And eventually, as you go through the length of the list and you do the bubble up algorithm, you'll get a sorted list. But this is not very um, this is not a very cost effective.
In the reversed.
Oh, why does it do it in the reverse direction? Okay, good question. So, it's for I in the range of length of the list.
Here, I
It
can
takes a
show you
list.
the example.
Yeah. Let's look at an example.
Like, so instead of insertion sort or selection sort, which always looks at the beginning of the list, this one is essentially like the name. You bubble up the largest value to the very end until it gets to the end. And you have to look through every pair until you've gone through the entire list and you've sorted the entire right side. It's I mean, I guess you could do it in the opposite way. This is just the way that bubble sort is defined, but you could do reverse bubble sort and it would be the same time complexity. Yeah, so like in this case, you're comparing 6 and 0. 6 is greater, so you switch 6 and 7. 7's the biggest. 7 and 5, you switch. 7 and 1, you switch. And then now 7 is at the very far right, and that's sorted. But then you keep going through it until you reach that last position. So there is no best or worst case scenario. Even if it's completely sorted already, you're going to check if 0, 1, 5, 6, and 7, you're still going to check 0 against all those values. Nothing will switch, but you're still making those comparisons. So that CPU load's still there. Does that make sense? Or better yet, does anybody have any questions about this? Where are we making helper functions for these sorts? The reason why we do that is just so that we like it's easier to read. You could have it all in one function, but it's just easier when you're testing, like unit testing, or you're going through and trying to debug what's going wrong. If somebody codes this and you're a secondary developer and you're looking back at this, it's just easier to kind of separate it. It's the same as like let's say you were looking at insertion sort. It's just easier to kind of pull it apart so that you don't need all of these comments in between explaining what's happening. It's always good to comment what you're doing, but this just gives it a way to show that it's like two separate parts. Yeah, you don't need the helper functions, but like the definition of them, they help to understand it or explain it to other people.
Yeah. Modularized code is always, well, not always, but modularized code is like good usually.
Yeah. And that is everything.
Yeah. Does anyone have any questions ending off, or was this clear?
Like we'll have a break and then we'll continue on. Don't worry. We
Yeah.
aren't actually done. This is just the final slide. What is the running time for bubble sort? It's quadratic. Yeah, so it's k times k. Just because you have to compare all the way through the list each time. I know it's like still like -1 each time because the right side's completely sorted, but it's still quadratic. Insertion sort, its best case scenario. Its best case scenario is linear because you only have to look through it once, but its worst case scenario is quadratic as well. You'll learn some more in A48 that are using like log n or n log n, and those are better. Because even though if the length of the list is really big, at some point it's still like a couple steps. Why we will use comparison to evaluate the running time of these sorting algorithms. I don't really know how to answer that question. Alex?
Why we will use comparison to evaluate the running time of these sorting algorithms. So okay, so maybe I didn't understand the question first off. So what exactly do you mean by why will we use comparison to evaluate the running time of these sorting algorithms?
It doesn't have to be comparisons. It can be like setting a value. I guess we're trying to see how many times the code is going to be run. Yeah, and for sorting, you're doing a lot of comparisons. Like the main operation that you do are comparisons, which is why we use those. I'm trying to think. Alex, can you think of any examples where you wouldn't use comparisons to find the time complexity?
To find the time complexity?
Yeah.
I think like a comparison counts as a step, so I guess you're counting like a comparison as a step, right? So the time complexity is just the amount of steps relative to your input. So I think the reason why you're just using comparisons is just that, well, like the comparison is like the main step you're doing. Like everything inside of like the while loop or the if loop's like another step, but mainly you just want to look at the amount of comparisons you're doing because, well, like that's the main step you're doing, right? The amount of stuff you have to compare. Maybe there's some other stuff you're doing after you've compared stuff, but the main thing you're focusing on is the amount of comparisons, because that's the main thing like a sorting algorithm does, right? Why doesn't the insertion sort have time sigma L plus one? Sigma,
To I, sorry.
oh, yeah. Sigma 2i plus 1. Um, why is there the extra comparison? Insertion sort?
Mm,
Why is there an extra comparison? Oh yeah, it's to stop the while loop. Yeah. Thank you.
oh, thank you. Yeah. Okay. I think this is a good time to take a break. Okay, sorry, I'm back. This is a good time to take a break, and then we will come back and we'll do some Open Your Wing 101. We're gonna go through uh the last exam. And I will send the slides in here as well. Okay, I'll be right back. Okay. I don't know if we're ready, but let's get into this. Okay. So can everybody see my screen? Yeah? Okay.
Yeah, I can see it.
So this is last year's exam from 2021. And essentially we're gonna try and go through this. We'll see how well this goes, but hopefully it goes well. Okay. So this first question, we've got to define a function, which means the header, the docstring, and the function body and the implementation. Our input is a file. So this is an example of a file that contains 0 or more orders made at various tables at a restaurant. Below is an example file on the left. So table 1 ordered an omelet, a coffee, and a croissant. Table 7 ordered 3, and then table 4 also ordered 3. Note that each table's order record begins with a line containing the table number, an integer, which is then followed by 0 or more menu items ordered.
Mohammed, the exam file is above it. We
Oh,
shared.
no.
Oh, she sent it. Oh, okay, yeah, she sent it through direct message.
Okay,
Yeah.
hold on 1 second. I will
Never
send you
mind.
this. Okay, so it was just sent. What is my example? Okay, and also here is the example for this text file to test with. So you can follow along. I'll share part 2 once we get to it. So essentially we want to take this text file, which has it has a number and then it has all the orders, and it doesn't have to be 3. It can be like 10, it can be 0, all the way until we reach an end, which is a keyword. And then we'll go on to the next one, or we'll reach the end of the file. And we want to convert it into this dictionary where the keys are the integers and they map out to a list of tuples, and each tuple is the menu item. I know that's a bit confusing, but this is what it's going to look like. So this is the menu item. It'll be a tuple. It'll have the string, so this ID of whatever you're ordering, the item, and then the name of it, and then what's in it, I guess. Just notes on it. It can be empty, and then the price of it. Okay, so let us start coding this. Alex, can you watch the chat?
Yeah.
Okay, thank you. Okay, so first things first, let's start with our menu item. We're going to define that. Oh, wait. There we go. We can really see it now. So just this one, you can actually just copy and paste this. Just so that we know what our format is going to be. And let's define this function. So part A, sorry, yeah, so we're getting there. This was just an explanation of what we're going to be implementing, and this is part A. So part A, question 1. Okay, so define a function read orders that takes an open file, which means we're not going to be opening or closing it, in the above format, so the menu item, as input, in the above format, so in this, and returns a dictionary where each key is the table number and each value is a list of menu items, so tuples, ordered at that table. See example output dictionary above, which is this. So this is our desired output. You don't need to sort the list of menu items. For full marks, your solution will be defined appropriate. Oh, your solution should define appropriate constants and helper functions. You do not need to provide examples in the doc strings for this function or any of its helpers. Okay, so first things first, how do we define a function in Python? Awesome. So def, we're going to need read underscore orders. So inside of here, it's going to take an open file. So we can just name it file text.io. Now we actually need to import this. So from typing import text.io. That's the only thing we're taking in. And then we want to return a dictionary. So dictionary, and we want to have each key is a table number. So that's going to be an integer. You can tell it's an integer from here. And that's going to map out to these menu items, but we want it to be a list of these menu items. So we're going to have list. And since we've already defined menu item, we can just put menu item. For this capital D and this capital L list, we can import those as well. Okay, so I know Anya really stresses upon this. We need to go through this doc string, so the explanation of what this function is going to be. So can anybody give me an example of what this function is doing? And we don't have to provide examples for the doc strings, but yeah, we do need an explanation. Yeah, for this read orders. Yeah. Usually what's really useful is to start with returns. But yeah, so a sample, give me a sample explanation for what this function does. Returns a dictionary where the keys are the table numbers and the value is a list of tuples, tuple containing the orders and the price. Awesome, yes. One thing to note for that one though, make sure you include, it's from file. So you want to include all of your different, parameters or your arguments. So, the difference between return or returns, in this case, it doesn't really matter in my opinion. I think you can do return or returns. I'm not sure whether or not one's plural or not. I think you can just do returns. Return, though, in the code is important because that's a keyword in Python. So yeah, so let's do that. So returns a dictionary where the keys are the table numbers and the value is a list of menu items. Should dict be dict from the newest Python format? The reason why I was using capital D, I'm not too sure about the difference. I know that lowercase dict is an actual, like it's defined in Python. Alex, do you know this?
Dict be dict. In the newest Python, I actually don't know much about the newest Python format.
Yeah.
In the version she used is she using like the newest one in this class, or is she using 3.6? And list is list.
The newest one is 3.11 actually.
Is she using that for this course, or just 3. Like the one she normally uses? She used
she
dict and
uses
list.
lowercase.
Okay.
So let's stick with what she's saying. You don't need to import it then. Yeah, I would follow what she says, so yeah, we can use
Yeah.
this too. Is a list of menu items formatted as item, and then we can use this over here. Yeah, and you'll want to do next. Yeah, okay. And then from here, this maps out to a tuple, string, string, which is in the definition on the right, from file. Okay. I hope she would approve this. But yeah, I know important thing, you need to include the parameters in here somehow, and then explain what it does. And usually start with returns or modifies. Okay, so to start this off, we're gonna need an accumulating variable. So since we're returning a dictionary, let's say orders equals an empty dictionary, and we're going to be adding to this dictionary. So we can really look at this example. I really like having it just on the side. So from here, the file is already opened. We don't need to open it. This first line is going to be 1, and then we're gonna keep going through. So out of the 3 possible options that we have read, which is like having it as a full string, or read lines, which converts it into a list of strings, or read line. What would you guys like to try? Or we can, yeah, I can choose one too. Yes, we do want to use for loops or while loops. So, okay, yeah. So I'll just go through what I did. So the first thing I did was I got this first line. And yeah, we want to make sure that it does not equal end. But remember, end happens after every order. So the only reason that it would be completely empty is if it's at the very end. Once you strip it, I think. Yeah. So there is an invisible /n, like backwards /n, on all of these lines, except for the last one. And that'll denote that we're at the end. So I'm going to define a variable. It's called table ID. It's going to be that first one. And I'm going to do file.readline.strip. Now the strip function is really important because, like I said, there's an invisible /n here. And if I don't, that can cause a lot of problems. And also we won't get our desired output. As well, readline is going to make it equal to a string. However, we want it to be an integer, so we can convert it here. You do int, and then you surround the entire thing. Is this making sense so far? Okay, awesome. Okay. So we're going to keep going through this entire file. I'm going to use a while loop, and while table ID does not equal an empty string, right? Because this is the first line, and we can have it equal to just no orders. So this is important. We're gonna read that first line. So we've already read this one. Now read line is looking at this order right here, which is really long. So we're going to get that item. We're going to do file dot read line dot strip. Remember the dot strip because there's that /n. And since there are several different orders, or there might be, we don't know, we're going to read this, and while item does not equal, just like Peter said, does not equal end, that keyword. And remember, this is important. I said end, not end/n, because we're stripping it. And one other thing, we want to make sure we haven't hit that end of the file. Now we're going to keep going through each of the orders until we get to the end. Okay, so for here, if we look at our format over here, we want each item to be in this tuple. We want it to be split up. And then we want to add it to this key in our order. So first off, how do we split up a string based on a delimiter? Yes, yeah, Muhammad's already got it and added here. So first things first, we're gonna do item and dot split. Yeah. Now we need to add it to two orders. So there's two scenarios, and this is kind of similar to what we did through the what's it called? Generating a story. If it already exists in orders, all we have to do is we need to append it to this already existing list. But if it doesn't exist, then we need to create it. So we need to test for that. We say if this table ID, which is the table that we're looking at, if it's in orders already, so it means it already exists, what do we do instead? Instead of just creating one, what do we do? Why is the item not equal to this? So this, Peter, it's just making sure that we don't reach the end of the file. Just in case. Honestly, you probably don't have to do that just because we're gonna have an end at the very end as well. But I just wanted to be cautious about that. We can test it both ways though. Append to the existing key. Awesome. So orders, remember table ID is going to be the key, and we're going to set it equal to, we want it to be a tuple. So all we can do is write tuple and then, oh, wait, yeah. Wait, nope, wrong way. Sorry. We're going to append this, not equal to, because it already exists. So if it's already in there, we just append it to the existing list as a tuple. Otherwise, we want to create that new key and make sure that you add it in a list. Can dictionary use append? Yes. Oh. So it depends what's in the dictionary. I'm actually appending it to the list. So I don't think dictionaries can use append. You might be able to. Maybe we can definitely try it. Alex, do you know if you can append to a dictionary?
I think you can. You just need to. If there's already a list in that spot, then yes. But I don't think you can like add on like keys and
Like
stuff.
just this.
Yeah.
I don't think you can do this.
I
It
don't
might
think that works.
contain.
No. That doesn't
Dictionary,
look like it works.
yeah. Okay, actually, I'm just like coding right through this. I want to make sure this is working. So, yeah, hold on. Okay, so to comment out really quickly, this is really handy and I learned it way too late. Hold control and then forward slash, and it'll comment everything that you're highlighting. So we will don't worry, we will uncomment this line by line. But I just want to see that it's working. So I want to print the table ID. That's about it. Oh, I guess I need to save this as well. Okay. So let's run this. Oh, you can't see it. Oh no. I don't know how to add another one. Hold on. I guess I don't know how to add it. Do you know how to add it?
If you just want to add on like more, like just more keys or
No, just the Python shell.
oh.
I might be able to close it here and then.
Oh yeah, right.
Yes.
No idea.
Okay. Oh yeah, you can, instead of writing tuple, you can write here. Although in this case, I would add it with the capital T just because that's in the function. And you can just import it from typing. Sorry, sometimes my computer lags. Sorry about that. Okay, so we've just ran it. Make sure, if you're coding along with this, make sure that your file, wherever it is, make sure it's in the same folder as your example.txt. So this one is just the same as this example. We're just going to go through it and make sure that it works. Okay, so for this, we can call read orders on our ex.txt. So right now, string object has no attribute. Oh, we have to open it first. So read orders, open ex.txt, comma, and we're gonna open it for reading, which is also the default. Okay, awesome. So this is how you know if your code is working. You should get a 1 back because that's the first order ID, and that's all we've done essentially. Okay. All right, so then let's uncomment out this one and this one, and we can try printing item just to see what that looks like. So you can run it again. What's really handy is you can just press the page up key, or like the arrow up, the upwards arrow key, and that can just go to whatever you coded last or whatever you typed in last. So if we try this again, oh yeah, okay. So fun fact, this is going to keep running because I made a mistake. Table ID isn't being rewritten. So table ID is always not going to be an empty string. Therefore, this is going to keep running for infinity. So what I'll do is I'll press options and I'll press restart shell. Yeah, so just to avoid that, I'm gonna make table ID equal to this, just so that we don't accidentally do that again. So if we run it again, it should equal just this first line, just because I've set table ID equal to this immediately. Obviously, we're not going to do this. We're going to keep going through all of them until we get to the end, and then it'll stop. But for now, I just set that equal. So make sure you're getting that first string. It's that first order, or that first item. Does anybody have any problems, or are we good to keep going? Are people following along? I should also ask that. Okay, okay. All right, we'll keep going then. All right, so you get rid of print item. Let's uncomment this next while item. You have to write again table ID. We will have to, but it'll be at the very end, and it'll be after this while loop. So essentially this while loop is going to go through all the orders until it reaches end, and then we're going to read the next line, and we'll go back to the top of the first while loop, which is why I labeled this table ID. So actually, if you want to get a little bit ahead, outside of this inner while loop, do table underscore ID equals file.readline dot strip. And don't worry if it's complaining, it's just because nothing's in this while loop, so it's like, oh, you need to tab it, but we will have stuff in here. So we're gonna split up this item. We're also, no, we should be good, yeah. Then we can uncomment these. So the while the item is not equal to end, why isn't the table underscore ID equal to end? The reason why is because we're going to read it again. So once once item is equal to end, then we're going to set table ID equal to that next one. Int table ID. Yes, you are right. Yes. Sorry, I do have to do that again. Convert it to int. Yeah. So, okay. Just to, yeah, we're almost done. So once we figure out whether or not it's in the table and in the dictionary, and we add it to orders, then we're going to set item equal to that next item. File.readline.strip. So let's go over this, okay? So from the very beginning, create cumulative variable. Get first table ID. This is looping over each table's order, right, until the very end. This line, item, get first item in table order, tables order. We don't need this anymore. Sorry, that was from testing earlier. This line, looping through each item in the order. So we're going to loop through A12, which is the omelet, B2, coffee, and then P3, which is croissant. We'll keep looping through there. Item, we're going to get the item, get item, and separate it, or create a list. Separated by the delimiter, semicolon. So for this if statement, if the order, or like if the table already exists in our dictionary, append our item to the existing list in tuple form. Make sure to convert it to tuple because that's what's requested here. Otherwise, this means we're starting a new table order. If the table doesn't exist, create a new list of items for this table. Yeah, and so it's a list, and then we add the tuple. Then this line, get next item, and this is inside the while loop. This is our last line. So we'll go back up to the top. Also note that if, let's say there's no order, for some reason there's just a table and they don't have any orders, what that means is item at the very beginning is already going to be equal to end. So this while loop, it's not even going to add that table to our orders, and it's just going to go and get the new table ID afterwards. Does that make sense why? Hopefully. Is it possible we do examine the computer for B level and above? I think we do. A couple of them we do. I can't remember if B07 was. Alex, do you remember if B07 was on the computer?
Oh, if the exam was on the computer, yeah. So when I took it, it was. Keep in mind we were online, so we had online exams, so that might change with in person. But when I took the course, we did have on, well, yeah. So we did have it on computer. But it might be different. It might be different now that it's in person. I don't know
Yeah.
how the courses run.
I think it is in person. Like, I think most of the exams will be in person. And then this last line, we will add one more line just to finalize it off or finish it off. But what this table ID is doing, assigning the new table. And then we go back to our original table. Last but not least, we want to return orders, which is our very last thing. That's our dictionary of integers. Hopefully this works, but let's test it. I'll zoom out just a little bit so you can see the entire function. I think that's it. Yeah, okay. Okay. So if we run this, instead of printing anything, it's not going to print something. So instead of just calling this function, we're going to want to type print whatever the output is. So invalid literal for int with base 10. This was probably the last one then, if it was empty. Yeah, that's why it's complaining. So it reached the end of the file, and then the file.readline.strip is that last one. So we could instead, we can add this file or this one, like this int part, we'll add it at the beginning. So table underscore ID equals int table underscore ID. Just so that this is whatever the regular one is, and then we don't get an error when we try to convert it. So if we run this again, we call it, you should get something like this. Yeah, and that's part A. That's only part A. Does anybody have any questions about this, or? Why do you use print? The reason why is because remember how I was talking, if you're creating a new one, or like during unit testing, you're creating a new list or a dictionary, or if you're modifying this. So for this one, we're creating a completely new orders, and then we're returning it. So when you call this function, it's not going to print anything unless you actually put the print function in there, like you call print orders. But in the real world, you're not going to want to leave print statements inside of your functions unless that's what the function's doing.
Yeah. Most of the time print statements are kind of used for like testing.
Yeah. So the reason why you could do like part A or part 1 equals read orders, open this. So you set equal to part 1, and then you can print part 1, and it should be the same. So why is table ID not equal to end? Okay, so we can actually, yeah, I think this is an important thing to go over. So let's say we change this, right? Like let's create a new one, okay? Let's call it, I don't know. Let's say table 1 has no orders. Table 3 has what's the format? Just gonna copy this one. It only has one item. And then let's say table 4 has like 6 or something. Okay, and then end. So let's call this EX1. Okay, so when we're going through this example, let's go through this. Table ID is going to be that first line. So it's going to be 1, and since we're stripping it, it doesn't have the /n. While table ID does not equal the empty string, table ID is now an integer, and the item is going to be that second line. So the second line is actually end, because this, for some reason, this table's order doesn't have any items. So item is equal to end. We stripped off that /n at the very end. And we're going to loop through each item in the order. Now, for this first one, item already equals end. So we're going to skip this whole while loop. And now table ID is going to equal file.readline. So it's actually going to equal 3. Since we're calling this readline function again, we're going down to the next line. It's not equal to end. And then we'll go back up to the top while table ID is not empty. So it's actually equal to 3. So we change it to an integer. Item equals, now it equals this first line. So this line is equal to item. While item does not equal end, this one doesn't equal end because it's the first item. It has an item in it. We split it up. We add it to our orders table. We get the next item. This item is going to equal end. So then we'll stop this inner while loop. And then table ID, when we call this readline again, is going to equal 4. And so there's never a case where table ID is going to be equal And yeah, we don't need this. I added it because I don't know. I added it just in case, but yeah, you don't need that. Because item will never equal that, because as soon as you reach end, it's always going to stop. Yeah, so even with this example, let's say, so I changed the name of it, so it's EX1. I'm gonna open it, and then if we print part 1, remember as well, it's not ordered, so I could do like 4, 3, and 1, and a dictionary is not ordered, so it wouldn't matter. But since 1 didn't have any orders, it wasn't added at all. And then we have 3, so we have the list of this avocado, this one item, and then 4 has like 6 in its list. So the item reads the next line, so it reads end, and the while loop stops. Yes, so this inner while loop stops right here. And then table ID reads the next line. So it'll never equal end. Item will always equal end, stop, and then table ID will be that next one, which is either going to be the end of the file or it's going to be the next table ID, just based on the format of how you're putting it in. Does that make sense? Hopefully. Note that each table's order record begins with a line that contains the table number in integer, which is then followed by 0 or more items, which is then followed by the word end on its own line. Yeah, that's in the definition over here, right here. Yep. Yeah, I should have said this. This review seminar might be a little bit longer. I might, I don't know, might do part 1 now, and then maybe later tonight or tomorrow might do another one. But if you guys are in it to win it, or if you guys want to keep going with me, I'll do all of this. So when it does not have orders is empty list. No, it's not even added. Because our logic to add to orders is only inside this while loop, it's not added at all and it's discarded. That's my implementation of it. If it says in here, if it's like if it says to add an empty list if there are no orders, then you could add right here. Right here, you could say, like you could use this. Actually, no, if it's already here, you could just do orders at position table ID equals an empty string or an empty list, and then you wouldn't even have to check whether or not it's in here because it will always be initialized here. But I don't think it was specified in here. I don't know. I might ask about that, but yeah. Yeah, you could do it this way. So if you wanted it here, like if you always wanted to have it an empty list if a table doesn't have orders, which doesn't really make sense, but you could do it, then you would initialize it here. But for this sake, I'm gonna keep it in the while loop because if there's no orders, then it doesn't really make sense to have any. If you guys are okay with it, we can move on to part B. Sorry, it is really dark. I'll be right back, 1 second. Okay, let's go on. Okay, so we're going to define a new function. It's called orders summary. And it's going to take in a dictionary as above as input. So we can honestly just copy this and paste it over here. We do need a name though, so we can say orders. And it returns a corresponding dictionary where each key is a menu item ID, which is a string, and each value is a number of orders made of that menu item. So it's going to be a dictionary. Each key is going to be the menu item ID, which is a string, and we're going to have an integer that maps to. So the way that I wrote it is returns a summary of the menu items that were ordered and how many according to the table's orders. And then I put orders because that's referring to the variable name. So to start, we're going to have to loop through each of these values and then look at this first position in each tuple, because it's always that, that format. So first, we want an accumulative variable because that's actually what we're going to return. So I said ID to orders, just set that equal to an empty dictionary. And we're going to loop through each order or each table, however you want to describe it. So for order in orders. So right now we're looking at a list. So every time that we reassign order, order is going to be this list. So we want to also look at for each item in orders at position order. Remember, this is a dictionary, so the keys are not like, you can't, you have to get the dictionary at that specific key. Now we want to get the menu item ID. And don't worry, if item is empty, then this for loop won't even run. So you know menu item ID has to exist if it's inside of this for loop. We're going to set it equal to item at position 0, because this will always be in the same format as defined here. And we want to check whether or not it's already existing in ID to orders. So if menu item ID is in ID to orders, then we can just add 1. So essentially we're just counting how many times it is ordered. This could be in a restaurant, this could be a practical scenario. So then we want to add it to menu item ID at position menu item, oh sorry, wait. ID to orders at position menu item ID, you add 1. This is just short notation for equals this long thing plus 1, or you can do plus equals. You cannot do plus plus though, just FYI, because this is Python. Otherwise, if it doesn't exist into it, then you need to create it. So we'll do menu item ID equals 1. And that's about it. Yeah, the only thing you have to do now is return the ID to orders. So something that I found useful was to just create like an example of what it should look like this at the top, so that we don't have to keep reading it and then opening it. So this is the exact same format, I just typed it out. If you try to copy it from here, Python, I had to learn this the hard way. Python doesn't realize that these little quotation marks are actually quotation marks, so I had to change them all. I wonder whether or not I can copy it into the text. Yeah, okay, so I just put it in the chat. So then we can run this. Y plus equals 1. Okay, yeah, so if the menu, so essentially in English, if this item is already in our dictionary, we want to add 1 to the amount of orders of that one item. So let's say you were ordering like an omelet or something, and another table also orders an omelet. You don't want to say, I ordered an omelet and I ordered an omelet. To the chef, you want to say, I ordered 2 omelets, or I need 2 omelets, instead of individualizing it. That's what this function is doing. It's the order summary. Yeah. So we just add 1 to wherever it's at. Otherwise, if it doesn't exist, so let's say, I don't know, I order an omelet and Alex orders a sandwich, we want to say, we ordered 1 sandwich and 1 omelet. We don't add those together because that wouldn't make sense. Okay. If we're good with this one, I'm going to the last part and then we can maybe, I don't know. If you want to take a small break, we can. Otherwise, we can go on to part 2. Alex, how are you holding up?
I'm holding up fine.
Okay, awesome. Okay, if there's no more questions, you can always put them in the chat, but let's go on to part C. I'll also just put a small comment that this is part B. Okay, so we're gonna define one more. Sorry, I just glitched. Define most expensive tables is gonna take that same dictionary. So you can just copy this one. And it's gonna return a list. A list sorted in non-decreasing order. So make sure you sort this one because lists are ordered. Of the number of tables that ordered the most expensive items. It's going to be a list of integers. Given the example dictionary above, the list should return the list 1 and 4. Now let me explain what that means. This is the example list that they're looking at. They're looking at what are the most expensive items. So just looking at this quickly, this is the most expensive item, and it's an omelet or A12. So since both 1 and 4, table 1 and table 4 ordered this item, then they added it to here. Now, just to make sure that we're sorting this, I'm gonna take table 4 and put it above 1 so that we don't forget to sort it. Yeah. Okay, so remember our description. We're going to return the table IDs, table ID or table IDs that bought the most expensive items in their order in orders. And I am going to add a prerequisite here. Prerequisite is that the item price is greater than 0. Otherwise, this won't really make sense. Oh, and we can also say there is at least 1 table in orders. Okay. So, first things off, we're going to create an accumulative variable. I'm going to call it expensy because expensive is long to type. So expensy tables, we're going to initialize it to an empty list. And we are also going to create another accumulative variable just to keep track of what is the most expensive item. Now, this is a really important part in part C. It says for full marks, your solution should look at each menu item in the input dictionary only once, which is why I'm keeping track of the most expensive item, or expensive, sorry, because I'll keep going through it, and when I find an item that's more expensive, all I'm going to do is I'm going to recreate expensive tables as an empty list, or as a list with that specific table number. Because all the previous tables haven't ordered an item as expensive as that one. So then we have a new list according to how many, like how expensive everything is. It'll make more sense when I go through it, but let's try it. So for order in orders, this is going to be each of the lists. And then we're going to look at for item in orders. The item price. How do you query the last, or sorry, not query. How do you get the last item, the last position in a list or a tuple? What index should it be at? -1. Awesome. Yep. So we're going to get this item price. Then we're going to compare whether or not it is more than the most expensive item that we've been keeping track so far. So if item price is greater than our most expensive item, then we're going to set the expensive item equal to the item price. And we're going to add to our expensive tables, or we're actually going to replace it with, we want it to be with the order or the table number. I think I might be doing this wrong. Instead of orders, it should be orders at position order. So for clarification, let's change, sorry, I'm changing it, but I'm changing it to table ID just because it makes more sense. And then we're going to add table ID. So sorry, I'll explain why I changed. So for table ID in orders, or table ID is, actually, I think, yeah, I'm pretty sure table ID is the key. Alex, can you correct me if I'm wrong or not?
Let me see. For table ID in orders, for item in orders, table ID, that seems fine so far.
You can, so to check
yeah.
this, let's
Yeah.
just call, like, let's just print the table ID. So most expensive tables, and then we're going to pass through our, I think it's example 1. If we do that, okay, so now we know table ID is 174 or 47417 because I changed the order, remember, so that we can check that it's sorting it. Okay, yeah, so table ID is good. How do we do this? How do you like undo this? Oh, okay. So fun fact, if you hold Control, Shift, and then /, it goes backwards instead, or it uncomments it. So For table ID, okay. Yeah, so we're gonna go through each table ID, and then we're going through each item. We get the item price. We compare, if it's greater than the expensive item, then we replace the expensive items, or the expensive tables, with the current table. And then we set the expensive item price to the new item price. But we want a list of all the tables that have ordered this. So what if the item price is equal to the expensive item? That means this table has also ordered the most expensive item that we know of so far. And we're going to just add it to our expensy tables. So we will append the table ID. And that's almost it. It's about it, yeah. So if it's, we found a more expensive item, so replace current values or current variables. We found a table that ordered the most expensive item. Last but not least, it does say we need to sort it. So remember list.sort, she even adds it in here. So we can say expensy tables dot sort. Now, important note to remember. She says it at the end, but this sorts the list and it returns none. This means that if you do this, you just lost all your data. Everything that you just worked for, expensy tables, is just going to be equal to none. So don't do this. Just make sure you call it. This is an example of a modifying function. So remember in the unit testing, we have returns a value or modifies the original value. This is modifying the original one. And then we can just return our expensive tables. So if we run this, most expensive tables, EX1. Oh, so since we're returning it, we need to print it. We will get 1 and 4. And this is correct because if we don't sort it, we're going to get 4 and 1. And I can show that by commenting this out. If we don't sort it and we run this exact same line, we're going to get 4 and 1. But she specifically said that she wants it sorted in non-decreasing order. Any questions, comments, concerns? So far, so good? Yeah. Awesome. Okay. Well, yeah, this is this whole thing. This is part 1. We do have exam part 2. How's everybody holding up? For the ELIF, what happens if we find a more expensive item and we've already appended to the tables? If we, I'm also a little tired. You're doing great though. What happens if we find a more expensive item and we already appended the tables? That's a good question, Peter. So if you look at line 87, if we do find a more expensive item, it'll just automatically replace everything. That's why this line is so important. You see how we're equaling it to a new list, a fully new list with just that new table. So in our example up here, let's say the most, like 7 is going to be the last one. Let's say T has it doesn't delete it, it just makes a new one and replaces the old one. Yeah. So let's say this became like a really expensive T for some reason, but it's the last item. So we can check what our most expensive table is so that For each table, let's print the expensive tables. If we run this, we will see that it's first 4 because $8.99. Then it'll be 4 and 1 because it's $8.99. And then we're going to see that whole thing is just replaced by 7. Actually, I think we might have to add it once more at the very end. So we run it. Yeah, so it'll be an empty list at first, right? And then we add 4 because it's got the most, and then 4, 1, and then it's replaced by 7. Oh, another cool thing. So this is debugging, but there's another way to debug. You can click, they have it in, yeah, they do. Okay, so in here, if you click on like the line right beside it, it'll stop the code when you're executing it at that line. And then you can see what the values are. So if we run this, and then we print the most expensive, oh, it doesn't show it? Alex, do you know how to do this? I was pretty sure you could. Or, oh, actually, I do understand. You have to call it in here.
Yeah.
Got you. Okay. Print most expensive tables x1. So now if we save this and we run this, oh my God. I don't know why it's not showing it. That's so sad. And then we print this. Just seeing how we can show this, because it's really cool. You can see the stack. Dang. I guess it's just printing it now. Oh, you were, yep. Yep, you're so right. Sorry. Yeah, so debug mode. Thank you. So it'll stop here. It'll show you, you go to stack data and it'll show you what each variable is. So like EX1, we have our dictionary. These are a ton of different things that you don't need to know right now. These are global variables that are just always active. And then we added our menu item and tuple we imported. And how you can keep going is you go to the next statement. So we called this function and it stopped there. So now we're going into most expensive tables and we're starting to execute this. So it stopped here because I added a point here. But at this specific point in the first iteration, these are the locals. So we have expensive item is equal to 0, expensive tables is equal to an empty list. And orders is this whole thing. If you keep going through, you can see table ID was just set because we started our for loop. If we go over once more, you can see this for loop has now started, so item is now defined. And yeah, it's really cool. You can keep going through it. And these different buttons do different things. This one, I think, goes over each line. And then this one goes to the next execution point. What if there are 2 most expensive items, same price? Then you just keep adding all the tables. Because they'll be the same price, so you just add them to the expensive tables. That's why it says here, it says the most expensive item, maybe like several. So if they're the same price, you just keep adding them to this table. But yeah, this is really useful if you want to see what each variable is at each step. And you can see how it adds. and it keeps going, and you can see whether or not the comparisons go through or not. It's really useful. Yeah, and then you'll see once we finish executing most expensive tables, locals just empties, because local variables, they're only created and stored while you are within the function. Otherwise, it gets erased and you can't access those again. So yeah, so then I just skipped over to the next breakpoint or execution point, and you can see locals is now empty and expensive tables equals 7. Yeah, just another cool way to debug. And you'll learn this in the future. Visual Studio Code is another IDE, which I really like and is very popular in the industry. There's also like PyCharm or IntelliJ. Those are also good. They all have these too. So yeah, just a cool debugging tip. Okay. But for now, is everybody doing okay? Like, do you want to go to part 2? Or do you want to take a small break? Can we do this tomorrow? Should be able to. Oh yeah. If you also have any questions about this, on the 6th, in 2 days, on Tuesday, I'm also hosting an exam study session for CSCA08 students. So make sure you sign up. But yeah, we can go over part 2 in there. Your TAs are also going to be there. So I'll send the registration link. But we'll have snacks and stuff. It's going to be a good time. Let me just find it 1 second. I don't know if you can, let me see. So this is where you can sign up. It's also in our Discord. And yeah, I can send part 2 if you guys want to work on that. Yeah, I think this will be a good place to stop. I can't do tomorrow, so if you guys are still good, we can do part 2 on Tuesday during the exam study session. Yeah, I hope this was helpful though. So I guess this is the end of our review seminar. We got through part 1. We got through all our slides too, and then
Yep.
Yeah, the part 2 has a lot of time complexity, but thank you everybody for coming and for
Thanks
sticking
everyone
with
for
it.
coming.
Yeah, the recording will be posted soon. I'll post both the Zoom one and the YouTube one just because Zoom deletes after a year. But yeah, good luck on your exams and hopefully see you on Tuesday.
Yep. See ya, everyone.
Bye.
Bye.